Dear ladies and gentlemen, welcome to my presentation entitled Using Heterogeneous Model Ensembles to Improve the Prediction of Yeast Contamination in Peppermint. At the beginning of the presentation, I want to give a short overview about the workflow of the presentation. I will start with the motivation of the topic. Then I will introduce the data, including some key numbers about the data. Then I will present you the general idea of the topic. Then the main part is how we identify the prediction models using machine learning and how we use those models to form heterogeneous model ensembles. Then I will introduce the evaluation matrix used within this project. And at the end, I will give you a short example of results. At the end, I will give a short conclusion and an outlook because this project is not finished yet. First, start with the motivation. We modeled the harvesting process of peppermint batches within a questionnaire, starting from the cultivation over the treatment, like fertilization, until the harvesting and the drying of the herbs. Then we receive information about the possible microbial contamination of yeast in the batches. Then we use different machine learning strategies to predict these microbial contamination, this yeast contamination. Within this prediction, we want to maximize the accuracy, but we also want to minimize the false negative rate so that no yeast contamination is overseen, which is worse than we predict a yeast contamination, but there would be no one, the false positive rate. So here are some key numbers about the data. The data is collected from 60 different farmers and is collected over 2 years. We have 81 different harvesting process features. We have 88 data entries, which result in 88 peppermint batches. Nearly 50% of them are contaminated and nearly 50% are not contaminated. The picture shows a short outlook of the questionnaire we prepared to collect the data, and it also the other screenshot shows possible output of a CSV file containing the preprocessed data. So now we come to the general idea of the problem, of solving the problem. So we combine the harvesting process data and the information about a possible microbial contamination with yeast to perform some main preprocessing steps. After the preprocessing, we train N models using 4 different machine learning algorithms. Then we evaluate each algorithm individually, calculating the accuracy, and we also form ensemble models combining the 4 algorithms. Here we use different strategies, which I will explain later. So this is the main idea of the solution. The slide shows a lot of information, which is the main part, the machine learning modeling and the strategies for the model ensembles. So first we start with 2 preprocessing steps. We checked for missing values and removed those features, or we filter we filter the data set using feature correlations. So we removed those features which have a high correlation to another feature. Then we used 4 different machine learning algorithms: random forest, gradient boosting trees, genetic programming, and support vector machines. For each algorithm, we trained 200 models with different parameter settings, which results in 800 heterogeneous models, 200 from each machine learning algorithm. To evaluate them individually and also to evaluate the model ensembles, we use 4-fold cross-validation. Then for forming model ensembles, we use 3 different strategies. First, we use all 800 models. to form a model ensemble. Then we use only 20%, the best 20% models. And at the end, we only use 10%, the 10% best models to form an ensemble. And for all these three strategies, in addition to the normal accuracy calculation, we also vary the classification threshold so we can optimize the prediction results even more. The graphic on the right side shows the basically process. So first we split the data up into, the picture shows 3 different machine learning algorithms. Then we train the models for each one, and then we combine those models into forming an ensemble, which hopefully performs better than the algorithms individual. So as I mentioned, I will introduce some basic evaluation matrices which are used to evaluate the models and also the ensembles. So we use different numerical measures like the accuracy, of course, but also the true positive rate, false positive rate, true negative rate, and also mentioned at the beginning the very important false negative rate, which shows us how much contaminations are overseen. In addition to that, we also calculate the positive predictive value and the F1 score. Besides those numerical measures, we also calculate the receiver operating characteristics curves, ROC curves, and also the area under those curves, which basically tells us how good our classifier works. So the example picture on the right side shows that the green line shows a nearly excellent performing classifier, and the blue line basically shows a worthless classifier, because the blue line, the false positive rate is always as high as the true positive rate. So basically the classifier does nothing else than guessing. And the best classifier would be a line in the upper left corner, but with 0 false positive and 1 true positive, which is basically impossible. But the curve shows how much false positive rate I accept to have a high enough true positive rate. So now we come to the results of the algorithm. So first we have the results of the single classifiers, which show that all of the 4 methods perform above the baseline, but not that much above the baseline. So basically not even 10% above the baseline. And the best one of the 4 individual classifiers is the random forest with 61.48%. And at the bottom we see the prediction results using the model ensemble classifiers. Here we have, of course, the same baseline. And the results immediately show that using all models and using the best 20% of all models results in worse accuracies than using the random forest individual. But then if we only use the best 10% of all models, we highly increase the accuracy by around 4% than using the random forest individual, which was the main goal of the whole project. And the next slide shows the threshold variation in more detail. So here we perfectly see that varying the threshold from 0.5 to 0.6 increases the accuracy a lot, and also increases the F1 score and reduces the false negative rate. So increasing the threshold to 0.7 would even more reduce the false negative rate to 10%, but also reduce the accuracy about 12%. So that would be make the classifier worse than better. But with a threshold of 0.6, we are good to go. And also we see the receiver operating characteristics of using 10% of the best models and using 20% of the best models, and then we see that the 10% model curve is far better. So it's more in the upper left corner than using 20%, but it's not the best. As I mentioned before, excellent classifier would have one curve which is in the upper left corner, but we currently can't achieve those good results. But using 10% results in far better classifier than 20%. So at the end, I will give a short conclusion and outlook. To conclude, we can say that forming heterogeneous ensembles of models leads to improved prediction results, predicting microbial contaminations in peppermint batches. As I mentioned before, the prediction performance is not yet sufficient for a real application scenario because also the heterogeneous ensembles is only slightly better than the baseline, but should be even better to be used in a real application scenario. But the main reason for this slightly bad results is mainly the databases, because the database is not big enough to exploit the full potential of the here blind methods. Because if we got even more data, then the results can be increased even further. So as I mentioned, we currently only have 88 data entries, which is not very much for a classic classification problem. So coming to the outlook, obviously we want to collect even more data to increase the databases. So the project is not over yet. So we're collecting more data and can use the same algorithms or even the improved algorithms with more data. In addition to use the same algorithm on more data, we want to also include more machine learning algorithms to the model ensemble process of machine learning models, like simple ones like the logistic regression, but also complexer ones like artificial neural networks. And in addition to that, we also want to apply the same approach for other herbs like nettle or apple mint or something like that, and also with different types of contamination. So for example, maybe we can predict mold even better than yeast or worse. So I want to thank you for your attention.